So, what are semiconductors? Well, we can infer from the name that they are semi, or sort of, conductive. So what does this mean? Well, it means that they are sometimes an insulator and sometimes a conductor. So they have a bit of a love-hate relationship with current. Well, how do they work? If we look at insulators first, insulators have only a few amount of these free-flowing charge carriers, in the case of atoms, electrons. This means that when we apply a current across them, these charge carriers are not very good at carrying current across the material. So when current tries to flow from one side of the material to the other, it can't very well, and the material resists the flow of current. However, there's no such thing as a perfect insulator. So if we were to apply a large current here, shown by the large amount of batteries, eventually the free electrons in the atoms would gain enough energy to allow current to flow. But this would often cause the material to break. So in the case of glass, you can make it a conductor by heating it up to a great amount, but often the glass will shatter before it's able to properly conduct electricity. So then what is a conductor? Well, conductors have much more of these free electrons here. So look, it's full of these free charge carrying electrons. So if we apply a voltage across it, same as before, there's much more of these charge carriers able to carry current, so that current can very easily flow across the material. And these are typically metals. So if we look at it graphically, you have insulators here who have a large band gap between the valence band and the conduction band. So these electrons that are down here require a lot of energy to jump up into the conduction band. So this is what we mean by band gap. Whereas conductors have a very small band gap, so it really doesn't require much energy for them to jump up into the conduction band. So what's the case then with semiconductors? Well, semiconductors are typically group 4 elements, such as silicon, so that when they are covalently bonded, as they are here, to each other, the group 4, meaning 4 electrons in that outer shell, are all bonded to neighboring atoms, meaning that there's no free charge carriers about the atomic structure. So then how do they conduct electricity? Well, there's two different types of semiconductors. There's N-type and there's P-type, and they are both made by a process called doping. So N-type, or negative type semiconductors, are doped with elements of atoms that have one extra electron, as you can see here, where silicon is typically doped with phosphorus, which is a group 5 element. And so when phosphorus is doped, what happens is atoms are added to the atomic structure of silicon. So we have silicon atoms all here with their 4 electrons in their outer shell all bonded. But when you add phosphorus to the mix, they bond in the same way covalently, except they leave an extra free charge carriers. So they add more charge carriers to the mix. And it's known as negative or N-type semiconductors because they add negative charge carriers in the form of electrons. So the other type of semiconductors, P-type, are then different, as they don't add an electron, but they take away an electron. So they are doped, typically, in the case of silicon, with boron, which is a group 3 element, so it has 3 electrons in its outer shell. So this leaves these electron holes in the atomic structure of silicon, and that's how it's known as positive doping, or P-type semiconductors, as the charge carriers in this case are electron holes which act as positive charge carriers, as the electrons that are typically in this structure will jump to fill the holes left by the boron, and the holes can effectively be thought of as positive charge carriers that can carry current. So in the case of semiconductors, a typical semiconductor you get are NP semiconductors, which is essentially just the N type and the P type stuck together. So if we have N type here with all its electrons all flowing freely around the atomic structure due to the doped phosphorus that's been added to it, and we have the P-type here with all its electron holes due to the boron that's been added. So what's going to happen here at the boundary? Well, some weird things are going to arise because you have a load of free electrons here and a load of electron holes. So what's going to happen is the electrons are going to jump into the holes across the border, which will cause the holes to be filled, obviously, and the free electrons to disappear. So then we see that this boundary here, that there is a zone of depletion, a depletion region as we call it, which is an area in the middle where there are no charge carriers. So on either side there are free charge carriers and could seemingly conduct electricity, whereas in the middle is insulative because of the lack of free charge carriers. These electrons here probably don't have quite enough energy to be able to jump over to the other side and fill these holes, but the ones close to the boundary do, leaving this depletion region. So what happens then if we attach a voltage across the NP semiconductor that we have here?
Well, the voltage that we have supplied from the battery here will supply the semiconductor with charge carriers, and also the charge carriers on the N side of this semiconductor with more energy. And so these electrons will start to gain enough energy to start to breach the gap of the depletion region here and reach the other side of the semiconductor, and in turn the positive terminal of the battery. And eventually enough of the charge carriers will have enough energy to entirely breach the gap, causing the depletion region to fully collapse and current to be able to flow throughout the material freely, making it fully conductive. But what would happen if we were to change the terminals of the battery, putting it in reverse bias?
Here, the opposite takes effect, and the electrons disappear from this side, and the holes also get filled on this side, which makes the depletion region larger here. So we have a larger depletion region, making the material less conductive, more resistant to current flowing. So what does that mean then? Well, that means we have a diode, because current can only flow in one direction. When it tries to flow in the other direction, it's met with high resistance and it's not allowed to flow, which is a useful property to have. And so why are semiconductors so important? Well, it's because they allow for controlled conduction, as we have seen. The more voltage you apply, the more conduction occurs. And this doesn't just have to be from voltage, it can also be from other sources of energy, such as light, heat, and electric fields. These all give the electrons enough energy to be able to jump across the boundary of the depletion zone between the N and the P sides of the semiconductor, allowing for conduction. Electric fields is especially important because this is commonly used in computers to make important components such as diodes and transistors, componentry you see here, which are crucial for electrical circuits and computers.